What up, crew? We got a little substitute for the 5-minute lesson here, and that's because I don't need to do any writing. This is the 5-minute lesson, and honestly, I'm just going to help you follow through with the book. So here I am in 3-5, limits at infinity. So what they want to, literally what they want is what happens when x approaches infinity. Okay, so think about it. If you had like a billion squared, and on the bottom you had a billion squared, those two numbers would be the same. So now on the top, you're talking about, I don't know, 3 times a number with, 24 zeros maybe. And on the bottom, just a number with 24 zeros and then a 1 at the end. Well, if you can imagine, the 1 is not going to make any difference to this fraction. Or that was a bad mathematical statement. Its difference is going to be so negligible that we don't even need to account for it. So you can really think about this question as 3x squared over x squared. And you're going to find that as you get higher and higher and higher, your table is going to start looking like this. As you go this way, it's going to start getting, look, even as we put 100 in for x, we already get 2.9997. And when we put a negative 100 in for x, we get 2.9997. So I hope from what you've been through in my class and being able to use your tables on your graphing calculator that you can see that as x approaches infinity, this limit of f of x is going to be 3. And what that is, you recognize this. This is a horizontal asymptote. It's a line that's not part of our graph, but that our graph gets closer and closer and closer to without ever hitting it. Remember that concept of if I started somewhere and stepped halfway closer to the wall, how many steps would it take to get me to the wall? Infinity steps, which means in that analogy, the wall would be my asymptote, okay? Notice this is how you write it. The limit as x approaches infinity of the function is 3. The limit as x approaches infinity, of negative infinity and positive infinity. All right, now next thing. If you see any questions that use this delta epsilon definition for the limit at infinity, skip it and come report it to me. Literally, my UC professor said, do not teach this. We don't teach it anymore. It's more confusing than it's worth. So that's important. Also, I don't think they teach it at Sycamore in the AP classes, and that's been a couple years. Okay? So we're not worried about this epsilon limit definition. So we're going to go on to the next part of the book. So now we have, for the first time in our life, we have a definition for a horizontal asymptote. If the line y equals L is a horizontal asymptote of the graph whenever the limit as x approaches infinity for that function is the term L. Okay? Feel free to watch this guy's video. It's old, but the math hasn't changed, and it's excellent. But I'm trying to kind of skip through it a little more quickly for you. Now let's look at this. If C is a constant and R is a real number that's positive, if you have a constant over x squared or x cubed, well, it's a rational number, okay? If the x is less than 0, then the limit is 0. Well, here, I'll help you with this. Here's what they want you to know. If we've been doing it this way since Algebra 2, you guys are ready for this. If you were to put infinity in for x, and x was at the bottom, you'd end up with 2 over infinity squared, which hopefully you start to realize that's 0. Okay, if you have 0 on the bottom, then your fraction turns into infinity. If you have infinity on the bottom, your fraction turns into 0. So the limit as this function approaches infinity is simply 5 minus 0. See, 5 minus, and that's 5. So that means the line y equals 5 is a horizontal asymptote for that function. And here you go. This is where you'll see that function. This is what it looks like. Now let's look at this one. Essentially, you've got infinity on the top, infinity on the bottom. These constants will not have a significant impact once we put in infinity. So you basically have 2 times infinity over infinity. Well, guess what? That's 2. Here's how you do it. Here's the math. Divide by everything in the numerator and the denominator by x. So 2x minus 1 over x and x plus 1 over x. So now 2x over x is just 2. Then you have a 1 minus x. X over x is just 1. Then you got a 1 over x. Well, now if you put in infinity for this right here, you're going to get a 0. If you put in infinity for x here, you're going to get a 0. So you end up getting 2 over 1. 2 over 1. But I want you to know, all you guys need to know for this whole unit is you can just put it in your calculator and start using your table feature on the ask function and put in bigger and bigger values or smaller and smaller values, and you guys will be able to figure this out. I honestly think we're almost done. So here, if we have a number that's higher power on the bottom, this thing is going to go to 0. If we have a number that's higher powered on top, this thing is going to go to infinity. If they're the same value later on in your calculus experience, and I can't exactly understand why we're not teaching you L'Hopital's rule right now, but you will learn L'Hopital's rule. But you should know that the answer for this one is 2/3. It's 2/3. Look, go down there, pause the video, and take a look. Okay, I think that's enough to have you be successful on the Unit 3.5. Hope you enjoyed this video. Shout out to Luca, Colin, Alex, and Carson, my faves. Malty, you guys will get your shout out tomorrow. Boom!